In the first chapter, we walk through AI's history. From Turing's thought experiments and Asimov's promises, through winters and breakthroughs, all the way to a layer of AI woven into daily life. But that story left three questions open. What is this intelligence really doing under the hood? What does it need in order to exist? And who controls each part of it? This second chapter is about opening the box. We'll see how an AI model actually thinks in numbers, how it learns from its own mistakes, and what it truly takes to keep it alive. What is artificial intelligence really? What we call artificial intelligence is, at its core, the field of computer science dedicated to creating systems capable of performing tasks we consider intelligent: learning, reasoning, perceiving, deciding. But beneath that academic definition hides something less elegant and more implacable. A factory of correlations that, without understanding anything, is capable of solving everything. A traditional computer is like a solitary virtuoso. It can execute extremely complex operations, but it does them one after another, in sequence, with almost military discipline. It is fast, but linear. Artificial intelligence, on the other hand, relies on hardware designed for multiplicity: GPUs and TPUs. They are not individual geniuses, but armies of mediocre mathematicians working in parallel. None stands out alone, but together they do something a single genius never could. They hold the entire problem in their hands at once. While the CPU solves one piece and moves to the next, the GPU sees everything at the same time. Every variable, every connection, every possibility, and crushes them all in a single coordinated blow. It is not faster thinking. It is a fundamentally different kind of thinking. But how does AI work internally? Every time you ask an AI to generate an image or translate a text, it sets in motion a ruthless mathematical ritual. Billions of matrix products firing in parallel, like a torrential rain where every drop at first falls chaotically, and then all that water is suddenly forced into a single, powerful river. If you tried to do it with a CPU, the operations would stack one after another in an endless queue. The result would arrive later than human patience. The GPU, on the other hand, breaks the problem into microscopic fragments, throws them to its thousands of cores, and resolves them almost simultaneously. What would be a procession of hours is compressed into milliseconds. Divide and conquer, sliced into microscopic pieces of computation. AI models are built by layers of digital neurons. To move information from one layer to another, a fundamental operation is required: the matrix product. It is the same operation that was used for years to render pixels in 3D video games, calculate lights, shadows, collisions. That is why we use graphics cards. They are specialized in this mathematical liturgy. The matrix product is the binder. It is the invisible glue that fuses millions of scattered signals into a single mental impression. It is the resin that hardens the concrete of digital consciousness. Without it, we would only have numerical islands, noise. But a binder like this doesn't float in the abstract. It needs very real muscles, memory, and cooling to keep it alive at scale. Let's now focus on how does this intelligence learn. Think about how a child learns to throw a ball into a basket. Nobody programs the exact angle of the arm, the force of the wrist, the curve of the fingers. The child throws, misses. The brain registers the distance between where the ball went and where it should have gone. It adjusts, slightly, automatically, and throws again. Miss, adjust, throw. After thousands of repetitions, something that started as random movement becomes precise, fluid, almost unconscious. An AI model learns in exactly the same way, except instead of a child and a basket, we have a network of digital neurons and a number, just one number, that measures how wrong the answer was. That number is called the loss, and it is the engine of everything. Here is how it works in practice. At the beginning, the model is essentially random. It has millions of internal parameters, numerical weights that connect each neuron to the next, all set to arbitrary values. You feed it a question. It produces an answer. The answer is almost certainly wrong. Not slightly wrong, completely, randomly wrong. The loss function measures that wrongness. It compares what the model said against what it should have said, and returns a single number, the distance between the two. A large number means the model is far from correct. A small number means it is getting close. Then comes the elegant part. That error, that measurement of failure, travels backwards through the entire network, through every layer, every connection, every weight. It finds each parameter that contributed to the mistake and nudges it by a fraction in the direction that would have produced a slightly better answer. This backward journey of the error is called backpropagation. Then the process repeats. New question, new answer, new error, new correction, billions of times. But scale has a price, a very real, very physical price. That sculpture does not exist in the abstract. It lives in silicon, copper, and gold. And what it needs to stay alive will surprise you. For the matrix products, the corrections, and the billions of cycles to become more than abstraction, they need a body, muscle, memory, and a way to survive their own heat. High-performance GPUs, led by NVIDIA, are the muscles of this creature. TPUs and other accelerators are added, designed for a single obsession, to execute matrix products on a colossal scale. These chips are built on monocrystalline silicon, crossed by microscopic rivers of copper and contact points coated in gold that resist corrosion. They are the organs where digital thought heats up until it brushes the thermal limit. Around those processors, like crowns of compact food, HBM memory chips from SK Hynix, Micron, and Samsung are stacked. They are vertical stacks of silicon connected with microsolders of indium, tin, and tungsten, capable of feeding the GPU with data at speeds impossible for conventional memories. Without this continuous flow, the digital neurons would run out of oxygen. That's why we need a cooling system, what we could consider the synthetic sweat. Modern data centers have been forced to gradually abandon air cooling and adopt liquid cooling systems. Cold plates attached directly to the processors, circuits that carry coolant to the heat source, and in some cases, entire servers submerged in dielectric liquid baths. The reason is simple. Liquid can carry much more heat than air, allowing power densities that would have destroyed any server room from a decade ago. These are not computer warehouses. They are liquid computing bunkers, thermal fortresses where deionized water and synthetic refrigerants circulate like cold blood, extracting heat from each chip, each memory module, each power line. From the outside, they look like anonymous boxes in an industrial park. Inside, the sound is a mix of distant fans, peristaltic pumps, and the constant hum of thousands of power supplies. They are capillaries of the silicon mind, and all of that synthetic anatomy runs on one fuel we can't backpropagate into existence: electricity. A lot of it. So this is what intelligence looks like once you open the box. Not metaphors, not magic. Millions of parameters correcting their own mistakes, billions of times over. Silicon that heats until it nearly melts. Liquid that runs through it like blood. But none of this exists in isolation. Every piece of it is built, mined, shipped, and powered by a chain that spans the entire planet. A chain with very real companies behind it, very real alliances, very real winners. And in the next chapter, we will follow that chain all the way up to find out exactly who sits at each link of it.